Isaac Newton's ingenious bucket experiment, though a thought experiment confined to the realm of the mind, remains a profound and enduring ripple in the vast pond of physics. Conceived to argue for the existence of absolute space, this seemingly simple scenario of a spinning bucket of water has sparked centuries of debate, influenced the development of fundamental theories, and continues to offer valuable insights into the intricate nature of motion and inertia. The experiment unfolds in stages, each designed to isolate and examine the relationship between motion, its observable effects, and the frame of reference. Initially, a bucket filled with water hangs motionless, its surface placid and flat. When the bucket is set into rotation by the untwisting of a suspended rope, a crucial dissociation occurs. The bucket spins, yet the water, initially clinging to its inertial state, remains relatively still. During this phase, there is relative motion between the container and its contents, but the water's surface remains undisturbed. However, this state of affairs is transient. Viscosity, the inherent stickiness of the fluid, acts as an intermediary, gradually transferring the bucket's rotational motion to the water. As the water begins to spin, a remarkable transformation takes place. Its once flat surface yields to a concave form, the water climbing the bucket's sides and dipping towards the center. This curvature, Newton argued, is a direct consequence of the centrifugal force acting on the water particles, a force that arises solely due to their rotation. The most compelling stage of the experiment arrives when the water and the bucket achieve a state of co-rotation. Here, the relative motion between them vanishes, yet the water's surface remains stubbornly concave. This, for Newton, was the crux of the argument. If the concavity was solely a result of relative motion, it should disappear when the relative motion ceases. Its continued presence, therefore, indicated that the water was still undergoing some form of true rotational motion, a motion not defined by its relationship to the bucket, but to an external absolute space. The final act of the thought experiment involves stopping the bucket while the water continues to spin due to inertia. The relative motion between the bucket and the water is re-established, but now in the opposite sense. Crucially, the water surface remains concave, further reinforcing Newton's contention that the observed effect, the curved surface and the associated centrifugal force, is tied to the water's absolute rotation, independent of its immediate surroundings. Newton's interpretation of the bucket experiment provided strong support for his concept of absolute space, a fixed, immutable backdrop against which all motion could be objectively measured. This idea was fundamental to his laws of motion and his understanding of the universe. However, this notion did not go unchallenged. Ernst Mach, centuries later, offered a powerful critique. He argued that inertia and the forces associated with accelerated motion, like the centrifugal force in the bucket, are not a consequence of motion relative to an empty, absolute space. Instead, Mach proposed that these phenomena arise from